Alright, in this second video we are going to go through some basic topology, finite countable and uncountable sets. Definition 16. Consider two sets A and B whose elements may be any objects whatsoever, and suppose that with each element x of A there is associated in some manner an element of B, which we denote by fx. Then f is said to be a function from A to B, or a mapping of A into B. The set A is called the domain, and f, we all say f is defined on A, and the elements of fx are called the values of f. The set of all values of f is called the range of f. Definition 17. Let A and B be two sets of and let f be mapping of A into B. If N contains A, f of A is defined by the set of all elements of x, for x belongs to E. We call f of E the image of f under f. In this notation, f of A is the range of f. It's clear that f A contains B if f and A equals B. We say that f maps A onto B. Basic concepts of functions. Definition 18, it's also related to the inverse of image, and of course, and it's an important consequence. It's what you know as one-to-one mapping of A. If you have such that if f of x1 is different from f of x2, whenever x1 is different of x2, so x1 belongs to A, x2 belongs to A as well, right? This is important to understand something that we called correspondence. If there is existing a one-to-one mapping of A onto B, we say that A and B can be put in one-to-one correspondence, or that A and B have the same cardinal number, or A and B are equivalent, and we write A is equivalent to B. Properties of equivalence, they are reflexive, symmetric, transitive, right? If that, let small n belongs to n and Jn be the set of whose elements are the integers 1 to 2n, and let J be the set consisting of all positive integers. For n set an, we say A is finite if A is equivalent of Jn for some n. A if A is infinite if A is not finite. Is countable if you can have the same cardinality between two numbers. If you cannot count, is uncountable. And if it's most countable, if A is finite or countable. Just one of these two. Remark 2. A is infinity if A is equivalent to one of its proper subsets. For example, if you ask me what are the size of what are the numbers of between 0 to 1, you have to realize that is the same number from 0 to plus infinity, right? So this remark 2, you can do this kind of stuff comparing to sets in the real number. By a sequence, we mean a function f defined on the set of J of all positive integers. If fn equals to xn for n belongs to J, it's customary to denote the sequence of f by the symbol in between brackets xn, or sometimes x1, x2, x3, so on. The values of f are called terms of the sequence. If A is a set, if x belongs to A, for all n j, then xn is said to be a sequence in A, or sequence of elements of A. Every infinite subset of a countable set is countable. Countable set represent the smallest infinity. Definition 22. Let n and omega be sets, and suppose that with each element of alpha of A is associated of subset of omega, we denote by E alpha. A collection of sets is denoted by, in between brackets, E alpha. The union of the sets is defined by equation 2. So you put all these units, it's not a problem. You can rewrite 12 in 13 and also in 14. The symbol infinity in both in 14 indicates the union of a countable collection. Please do not make this confusion between infinity here, because it's n goes forever, and the symbols plus infinity and minus infinity introducing definition 13. It's slightly different. The intersections between two n sets can be given by 15. You can write 15 as well in 16 or in 17 as well. The theorem 5, it's because if you have a sequence of countable sets, you can put in the equation 18. The set of all rational numbers is countable. That's something that I really like to you to think, you know. The set of all rational numbers is countable. However, the set of all real numbers is uncountable. To be honest with you, I have to confess that I accept this. You can find these numbers in the mainstream textbooks on mathematical analysis, but I'm not happy with this sequence. If any of you guys that are listening to this class, you can also agree with me, please let's discuss, because to my mind I'm not quite happy with this. But put it again, the mainstream textbooks, you can go to this sort of sequence. The set of rational numbers is countable, and the set of real numbers is uncountable. Definition 25 is just to say about metric space. So the distance between P and Q, now you can put these three definitions here. And the segment N and B, we mean the set of real numbers such that A is smaller than X and B, an interval between two numbers N and B. Definition 26 and 27, it's quite important, because when you are going to a computer, what you have in fact are some interval between these numbers, and what a computer do is not the same thing that you are going to do in a real number. And if you realize that what you have in a computer is an interval, it's much easier to understand that this interval is as in definition 27. You can say that you can make a ball B with center X defined by this definition 28. If you put this in a convex way, you can manipulate as this equation here, the 29, and you can say that balls are convex as well, because you can make this manipulation here as this convex here for all the numbers, right? So some definitions here, it's quite important, but I would like to concentrate some points here, most of all to understand what you have in the computer. So the neighborhood is a small portion of real numbers around the number. A point P is limit point if every neighborhood of P contains a point Q different of P, such that. So what you have, you don't have a limit point in a computer. What you have in a computer, you have isolated point, because this, for me, of all these definitions, is the most important point, because we don't have limit point, we just have isolated point. These are the definitions I'd like you to read, and if you have some doubts, please, you can get in touch, right? So let's put here from definition 31. If X is a metric space and E contains X, E denotes the set of all limit points. So this is a closure when you get what is inside and the cover of this set. If X is a metric space, so A contains X, so you have trash is slash E here is closed, E equals E if and only if E is closed. E contains F for every closed set. F contains X, such that E contains F as well. Let E be non-empty set of real numbers which is bound above. If I is supreme equals to supreme of E, then Y belongs to dash E here as well. Hence, Y belongs to E if E is closed. Compact sets. By the number cover of set E in a matrix space X, we mean a collection G of open subsets. So you can have a compact number if a compact set. So we have here it's a sort of many subsets as well. Definition 34. You have compact just if it's a closed and bounded. Here's something important in definition 35. If you have a sequence of a non-empty compact set such that Kn contains Kn plus 1, so you are going to n forever, you are not going to reach an empty set. In fact, you can use definition 35 here in many problems of optimization and also to see some convergence of numbers. You can do the same thing is a sequence of intervals, so it's really important this sort of sequence definition, because with this definition here you can use theorem 8 and theorem 9 to understand what's going on in a computer to prove some sort of convergence, right? A perfect set, so theorem 10, let B be a non-perfect set R Q, then P is uncountable. Every interval AB, and being A is smaller than B, is uncountable. In particular, the set of all real numbers is uncountable. Using some concepts of the German mathematician George Cantor, the ternary set is created by repeatedly deleting the open middle thirds of all sets in overline segments. If you do that, you can start with an interval of 0, 1, leaving mark 2 points, 1 divided by 3, 2 by 3. You can take the segments between them and go so on. A picture of this you can see like that. So the first segment is 0 to 1. You can take out the middle third and you go on so ever. You can go this sort of compact sets, and that's it's a proof that you can get a non-empty set and an infinity number, and this kind of proof, right? Connect set is just to see if you don't have a separate subsets. It's not so complicated to see, even in the theorem 11 as well, right? I'd like most of all to use the previous knowledge to think about these two questions. First of all, prove that the set of all real numbers is uncountable. Look for the strategy developed by George Cantor, usually called as Cantor's diagonal argument. And also I'd like to use the equation 19 to compute the square root using some computing language. I'd like to use MATLAB or Octave or Python and try to understand what's going on. So we should start with these numbers here to try to calculate the square root using a equals 2 and all this number here, and check your results. Make xn times xn. Use a suitable stop criteria. So make a use of a small program and try to see what's going on, most of all when you are using these small numbers. Try just one condition to use to compute the number 2. Please use a float point with 64 bits of precision, right? So okay, thank you again for the attention of this second slide, for the second video, and I hope that you can enjoy this course. Bye, and this is the end of this video, and in the next video we are going to continue a little bit more about mathematical analysis.